Well, I got a doozy of an update for you. Hi, I'm James Hutchison. I've been doing research on the theory of everything. I believe I found it. Um, I've been trying to find experiments that this theory would predict. And to do that, I'm trying to step out of areas that I really have much knowledge in and make a prediction based off of how I think things should work and see whether, hey, like, does it actually work that way? Um, the big distinguishment between this theory and others is the fact that these are directed fields. And in my previous video, I talked about how there was this effect called tunneling. The best analog I can find to tunneling is laser-induced self-focusing. And this is part 2, so this is a follow-up on that tunneling research. Now, tunnels get their name from their appearance in the simulator. So one thing that I mentioned in the first video is that one-directional tunnels are less stable than bidirectional tunnels. And this is because of the way it displaces the field around it, the shape that it makes. Another component to it is that tunnels next to each other are more stable than just a single tunnel by itself. So this can actually induce the appearance of a wave or interference pattern based off of how these tunnels form. I came up with 2 experiments to look for this tunneling effect. The first one would be at a climate scale and would look for evidence of it in climate data. The second one would be looking at starlight as it breaks through the atmosphere and arrives to us. It occurred to me that maybe what is happening is that these tunnels cannot form because of the dispersion of light in the atmosphere. And so when that light dies down, it allows them to do their thing. For my climate research, I pulled data from Ukavivik, Alaska, formerly known as Barrow, to see if there's any evidence of this tunneling effect happening there. Now, if there was, what I would expect to see is a bit more consistency in the peak values of sunlight hitting that area while the ice is there and hasn't melted. Once the ice is melted, I would expect a lot more variance because you would have a lot more unidirectional tunneling happening, and that tunneling would fall apart a lot easier. Other side effects might be just increased sunlight and sunlight occurring earlier. And I would expect to see that because as the ice caps melt and the extent of ice decreases over time, I would expect to see that there's now less area essentially competing for the sunlight, and it'd be a lot more directed. I might have this all thought about wrong, but that was essentially the hypothesis. I'd expect to see something somewhat similar on the South Pole, but I'm also not as familiar with what the South Pole station would have. And I'd expect to see potentially even the inverse on the stuff that's a lot closer to the equator. But I'm not fully sure on that. Starting with Barrow's data, you can see where the melt occurs because of the rapid decline in upwelling. You can also see a stretch during the spring where the upwelling is more consistent, especially in recent history. Green is recent data, yellow is about a decade old, and blue is about 20 years old. Downwelling data shows a very clear and steady line in the spring, especially recently. When you overlay the two, a strong correlation between incoming light and a decrease in upwelling forms. It also coincidentally aligns with when you would expect light to decrease due to the axial tilt of the Earth. One must consider whether this coincidence is not actually a coincidence, and rather maybe this electromagnetic effect on the North Pole actually helps set the speed that the Earth rotates. If you compare Earth to Venus, Venus has basically very high albedo, and it is very hot. Additionally, it also has a spin that runs backwards from the rest of the solar system, and that spin is very slow. It could also imply that the Earth's changes in spin are also electromagnetically induced. If you compare the other stations, you can see that Barrow clearly shows this before and after pattern. The South Pole, SPO, is always rather narrow. Mauna Loa and Samoa are always rather variable. All 4 stations also show the same pattern, at P99 values, there's more consistency and a decline in peaks, suggesting that this tunnel between the Earth and the Sun has strengthened over recent history. Or maybe it's something else like changing out equipment. It's hard to say without more research. Just in case it's our imagination, we can focus in on the first 4 years and last 4 years of data for Barrow and see with a clear graph that there's definitely less variance in recent history. We also see evidence that this connection is stronger by the delay from when ice melts to when variance increases. Alright, so now let's go back to the starlight research. Recall that this is where starlight comes in, and it's dusk, and it should be bright enough for a star to be seen, but for whatever reason, it's not there. And of course, stars also twinkle, so maybe that's a factor to the whole thing. It turns out that this is a known phenomena, and it's been documented, and there's a couple explanations that float around. One of them is quite old, and that is that it's simply atmospheric diffusion, and that your eyes are incapable of seeing something with that little of a difference. Basically, your eye kind of looks at it like it as an error and tries to like get rid of it. But I know that when I look at the star, I can see it, and once I see it, I shouldn't actually lose that focus, and it definitely happens. So that one is not right. Now, other things that have come up is it's just atmospheric diffusion, and because you have these light photons that are so far away, they are easily scattered. And again, it doesn't quite add up, and it's very frustrating to read this stuff online and then like imagine how it would look in your head, and you go like, it wouldn't look like that. So like if it was pure diffusion, it would look like a sphere, right? And maybe that sphere would like wobble like, you know, heat waves above the pavement, but it otherwise would not look like what stars look like, and I will show this to you. So first off, this is what a star looks like when it's out of focus. As you can see, it's spherical. In focus, a star looks fuzzy. There's a thick, consistent line, and the fuzz constantly changes shape around it. Adjusting our focus, we can't really get that to go away. You can see in this still frame that the star has a definitive plus shape to it. As we let less light in, we can see that there's a general focus around the center of the star, but not always. If we zoom in on our light, we can see that it definitively forms what appears to be almost an interference pattern, except light doesn't quite work that way. Another screen grab shows no interference pattern. With the star barely peaking, one can see a dominant tunnel and two periphery ones that are at 90-degree angles. Any light caught between the primary and periphery tunnels would be directed towards one or the other. In other words, a radiation pressure median, if you will, would form between the tunnels, steering light into a channel. In the simulator, it's difficult to maintain a unidirectional channel, but you can see that the effect is definitely there. And it explains why the channels are so random, is that they quickly fall apart and then likely reform again. Now, in quantum physics, wave-particle duality means that photons move in a path that resembles a wave, but there's always a particle there. And this aligns perfectly with that. You create what appears to be a wave interference pattern, and you get all your photons kind of funneled into these channels, and the odds of them being in the center of the channel is greater than the odds of them being on the edge. If we look at this older footage that I have when I was capturing Jupiter and its moons, you can see that the moons are a lot more random and erratic. This is behavior that is what I would expect if there wasn't any self-focusing going on. So to recap, we have two experiments that support the theory, further creating even more evidence that yes, this really is the theory of everything. However, there is, of course, always a due diligence step. And so there's a lot of factors that might cause us to see things that maybe aren't what we thought. So it's really important to not jump to conclusions, but this is, of course, a very exciting step forward. Thanks for watching, and remember to like and subscribe.